space that I think very. Sorry, did someone say something on Zoom?
I just started the recording.
Okay, thank you. Okay, so I want to report on a perspective on superspace that is particularly useful for twisted supergravity, and maybe I can convince you that the supergravity theories and its twists are maybe not as, are maybe more similar than you might anticipate at first thought. Okay, so all I'm going to say is based on two papers that I wrote with Ingmar Algebraic and Sayara Grandrun and Brian Williams. It also builds on earlier work with some of these other. So maybe a bit of motivation. So one interesting thing about supersymmetric field theories is that they contain certain subsectors, and these subsectors are sensitive to topological and holomorphic structures on spacetime. Of course, these subsectors can be extracted by the twisting procedure, which roughly goes like this. So you have a supersymmetric field theory. It has a super Lie algebra of symmetries. You pick an odd supercharge which squares to zero, so it has size bracket 0. Then this odd supercharge, it spans like a one-dimensional odd abelian subalgebra, and then you just take invariance with respect to that subalgebra. In that way, you get the twisted theory, and it has many nice properties. First, they're topological holomorphic field theories, and in that sense, they're much simpler than the full theory. They contain less degrees of freedom. In addition, like usually these holomorphic field theories, for example, can be formulated in terms of geometric moduli structures on spacetime, so they have nice mathematical and geometric interpretation. And then there's of course much more. There you have some good behavior under quantization. You can prove like one loop exactness results. You have like nice infinite dimensional symmetry enhancement, and you have twisted holography, and we can go on and on. However, usually, at least if supergravity is concerned, or if you like want to study more complicated examples of supersymmetric field theories, calculating twists can be quite hard. So what is the reason for this? Like one reason for this is that the supersymmetry transformation usually act on the fields in a quite complicated way. In particular, the action of the supersymmetries might be only on shell. In like mathematical terms, this means that the BV fields of the theory only have an L-infinity module structure for the super Poincare algebra, and not like a strict Lie module structure. And that means that, I mean, taking invariance with respect to such an L-infinity module structure can be quite complicated. And that means that investigating these twisted theories in target space has been, at least for supergravity, quite difficult for some time. And Costello and Lee, for example, arrived at their conjectures for twisted supergravity theories using like more topological string theory methods, where you first imagine twisting the worldsheet, and then you construct the target space supergravity theory associated to the topological like string theory. And then if you want to say something about 11-dimensional supergravity, you don't really have such a worldsheet picture. So the only thing you can rely on with these methods are like known results from 10-dimension, and then the various dualities and limits that relate 11-dimensional supergravity to the 10-dimensional theories. However, kind of the punchline is that if you work in superspace, the supersymmetries act in a purely geometric way. Like there is a strict action, and they just act via some odd vector fields. And then twisting just means taking invariance with respect to some particular odd vector field, and it's much more akin to like dimensional reduction, just that you now have like this odd direction, and therefore one might hope that if one finds an appropriate way to work in superspace in such a setting, then twisting becomes a lot easier. Okay, so here's the plan of what I'm trying to explain today. first I want to introduce some geometric descriptions of twisted supersymmetric multiplets from the pure spinor superfields, and these will be precisely these supergeometric descriptions on superspace that are perfectly well suited for twisting and that we can use to learn something about twisted supergravity from a target space perspective. And then I want to apply this to two different things. Like first, I want to explain how 11-dimensional supergravity and all its twists can be constructed as what I call homotopy Poisson Chern Simon's theory in a uniform way. And then I want to do a second thing where I discuss conformal supergravity and relate it to to a geometric modular problem of deformations of superspace. Okay, so let's start by discussing our supergeometric setting. So the geometric structures I'm interested in are the following. So we take M to be a supermanifold and we fix a distribution in the tangent module, so just a subbundle of the tangent module. Then for each point P of the manifold, we can define a filtration of the tangent space associated to this point by just taking successive commutators and evaluating at the point P. So the KFPs of this filtration is just given by taking at most K commutators or vector fields inside sections of D and then evaluating at the point P. So this filtration does not yet define a Lie algebra structure on the tangent space at the point P, because of course the commutator between two vector fields depends on like neighborhood around P, but the associated graded of this filtration actually does define a graded Lie algebra structure on the tangent space, and we call this the symbol algebra of the distribution. Just to introduce somewhat terminology, if we fix any positively graded super Lie algebra, we say that a distribution is regular of type n if all its symbol algebras are isomorphic to this one fixed super Lie algebra. And then we also call the distribution bracket generating if this filtration exhausts the tangent space for all points. And I just want to remark that these structures have been around in the literature for some time. For example, Mahnen called like a superconformal structure. He defined a superconformal structure to be like an odd distribution in a supermanifold where the symbol algebra is some kind of super translation algebra, which is also bracket generating. Let me introduce two, or maybe one, depending on how you count, motivational examples that come from complex geometry and that will be kind of guiding principles for what we will try to do in the supergeometric setting. So of course, if you take a complex manifold, then the tangent space splits into holomorphic and anti-holomorphic directions. We can just set the distribution to be the anti-holomorphic directions, and then in this case, of course, this distribution is involutive, and the symbol algebra is abelian. However, if you generalize and take M to be an almost complex manifold, then if this is like a true almost complex structure, then the symbol algebra is no longer abelian, and it's precisely the structure constants of the symbol algebra are induced from the 9-Gauss tensor. The main focus in our supergeometric setting are symbol algebras where, are cases where the symbol algebra is a super Lie algebra that is constant, that can be given consistent Z grading so that the super Lie algebra are concentrated in degree 1 and 2. So if we have like such a super Lie algebra n, we write it as n1 plus n2, and the only interesting bracket is given by a map gamma, which goes from the symmetric square of n1 to n2. And we also introduce G, which is just n, but now enlarged by some automorphisms in degree 0. And the running example that you should have in the back of your head super Poincare algebras where G0 is just some special orthogonal Lie algebra and some R symmetry. And then N1 is like the spin representation, and N2 is the vector representation. All right. So, and given such super Lie algebra that we want to see as symbol algebra, we can associate like the obvious geometric setting, which realizes this in terms of the distribution. You might want to call this the kind of model geometry or the flat model by just exponentiating this super Lie algebra to a super Lie group, and then to take the distribution to be spanned by right invariant vector fields. Explicitly, you can write this down in coordinates. So if you choose coordinates x and theta on n, then right and left invariant vector fields are spanned by these two formulas that you might recognize from physics, where they're usually called like the supersymmetric covariant derivative. So these span these kind of distribution, and this is like the explicit realization of this kind of flat model. Now, what we want to do is we can consider differential forms on the on this supermanifold N, and then if we write them in this kind of frame adapted to this distribution, which is defined by these kind of coordinates, we see that this distribution induces an additional z grading on differential forms, which is just dual to the grading induced in the tangent space. And then the Durand differential splits into three kind of terms here. We have terms of weight 1, 0, and -1 in this kind of thing here. And if you know something about pure spin superfields, then this already looks kind of suspicious, because the D1 term precisely looks as if it imposes the pure spinor constraint on these variables lambda, and the D0 term precisely looks like the kind of pure spinor differential that you usually see. But even if you know nothing about pure spinor superfields and haven't heard that term yet, we can recognize that this situation is somewhat analogous to our motivating examples that concerned almost complex structures. So if you have an almost complex manifold, you can do the following construction, which is due to Jerichi and Wilson. You can equip differential forms on the almost complex manifold with a particular grading where you put dz in degree -1 and dz bar in degree 0. And then the Durand differential on that manifold splits into 4 pieces, where you have the usual del bar and del differentials, but you also have additional pieces which now come from the Nijenhuis tensor and precisely encode the non-involutivity of the distribution that you choose. Now, what if you want to define the analog of the Dolbeault complex? You have to work a little bit for this here, because the del bar differential now no longer squares to 0, but it squares to 0 precisely up to mu exact terms. So what you can do is you can consider the spectral sequence where you first take homology with respect to the weight 1 piece, so which is called mu here, and then you define this WK, which is just given by the K of cohomology with respect to mu. And then if you have this is kind of the generalization of like K comma star forms to an almost complex manifold. And then the del bar differential descends to a differential on WK comma bullet, so that you can consider for example, 0 comma star forms with the Dolbeault differential. So this is this kind of generalization, and we can do precisely the same thing in our supergeometric setting. We can just set this WK to be the Kth cohomology of differential forms on n now with respect to this differential d1. But recall that this differential d1 was precisely encoding this constraint that lambda gamma lambda is 0. So for k equals 0, we precisely find that this differential d1 imposes the pure spinor constraint, so that we find w, like the analog thing of 0, star forms, is precisely just functions on n tensored with this quotient ring R mod I, where R is just polynomials in lambda and I is the ideal imposing this constraint. Yes.
What conformal have like higher?
Yeah. You mean like higher WKs?
Yes.
Yeah, they exist. And we will actually, I will have examples on that. Yeah. Yeah, so and this is precisely what physicists would call the pure spinor superfield. So it's the like generalization of 0, star forms on this kind of superspace which is equipped with such a distribution. Right. So now if you think about like complex manifold, of course, the appropriate structure sheaf on a complex manifold is the sheaf of holomorphic functions and not the sheaf of smooth functions. And it like the 0, star forms are like a derived replacement for holomorphic functions. In this sense, this generalization of 0, star forms that we constructed just a minute ago, or we like explained the construction of Chirici and Williams, are the appropriate derived replacement of holomorphic functions on like an almost complex manifold in that sense. And in this sense, I want to make the case that this A bullet is precisely the appropriate structure sheet that you should take if you think about such a superspace, which is equipped with such a like regular distribution of type n, where n is like such a kind of supertranslation algebra that I introduced in the beginning. In this sense, one should maybe view like a superspace as kind of a DG ring space where this A bullet, which is the pure spinor superfield, is the kind of structure sheaf on this space. And this is kind of the geometric perspective I want to take and during the rest of the talk. And so the first punchline kind of is that this pure spinor superfield precisely arises very naturally in this kind of geometric setting where you have such a superspace equipped with such a distribution. Now, of course, you can take your list of super Poincare algebras with like various dimensions and various amounts of supersymmetries, and then you can construct this structure sheaf A bullet, and you can study its field contents, and then you find various multiplets that we know and love from the physics literature. For example, in 4D n=1, you find the like vector multiplet or the BRST formulation of the vector multiplet. But for example, in the 11th dimension, you find the BV complex of the 11th-dimensional supergravity multiplet. If you really buy into this perspective that this WK is analogous to K, star forms in some kind of complex manifold, you can also define like some kind of holomorphic dimension of this superspace, where the holomorphic dimension is precisely the K, the largest number K, so such that WK is non-zero. I mean, this is precisely your question. And you can compute these numbers, and I will explain how to compute them in a minute. And then you find, for example, in the 11th dimension, you find that this like kind of holomorphic dimension of the superspace is 2. And then you can also think about what like the analogous thing to a Calabi-Yau structure in such a superspace is. Like if you have this WK, which is like a Calabi-Yau structure would be precisely like an isomorphism between WK and WD minus K, and you can investigate if such an isomorphism exists, and for example, in 11-dimensional supersymmetries, such a thing exists. So this is already like a hint that this perspective on superspace equips this kind of 11-dimensional n=1 superspace with a structure which looks very similar to what we would call like a Calabi-Yau twofold in complex geometry. All right, but you can even do something more general.
Fabian, could I interrupt
Yes.
there and ask a question? Yeah. So, what resolution do you have on what the Calabi-Yau twofold would be? I mean, is this just an abstract? Is this just an abstract description of a structure that could be compatible with the Calabi-Yau twofold geometrically, or can you case by case identify a Calabi-Yau twofold that is associated to this structure?
No, I cannot identify like specific Calabi-Yau twofolds. I'm just saying that this is kind of like a supergeometric thing which looks very much analogous to a Calabi-Yau twofold in this setting.
Okay, and by twofold you mean two real dimensions or two complex dimensions?
Two complex dimensions. So
I see.
So in this,
so we might be looking for an abelian surface or a K3 surface in concrete terms if it's compact.
Yeah.
Okay, thank you.
Right. Okay, so if you have this thing, a bullet, the pure spinor superfield, and you view it as this kind of structure sheaf on this superspace, now viewed as a DG ring space, you can actually turn this into a functor by taking like just the pure spinor superfield and tensoring it with a module over this ring R mod I. So this then gives a functor from R mod I modules, which are equivariant under this Lie algebra G0, and from this you can build a G multiplet. So this kind of generalizes this construction. And if you do this, you can actually describe the what I introduced as K, star forms, this WK, more explicitly. Namely, these WKs, these are in the essential image of this functor. And if you take your supertranslation algebra and let HK to be the K Lie algebra cohomology of N, then this WK is precisely this functor applied to this R mod I module. All right, so, and this also tells you how to compute these numbers of the holomorphic dimension. It's just a computation of Lie algebra cohomology for this particular supertranslation algebra. All right, but there is even more, but this is more just a remark at this point. We won't need this too much, but this is due to a paper I wrote with Chris Elliott and Ingmar. You can even do a further generalization of this kind of formalism where you replace the category of R mod I modules in this functor by the category of modules over Lie algebra modules over Lie algebra cochains of N. And then there is kind of a generalization of this procedure that associates like a multiplet to any C-bool of N module. And then this functor is actually an equivalence of category. And the inverse is precisely given by taking derived invariance with respect to this, with respect to the supertranslation algebra. And this diagram then commutes. So you actually can construct all kinds of multiplets from this such kind of input data. All right, but I promised something on twisted supergravity and twisting. So let's actually get to it. Namely, one can show that this kind of pure spinor construction is compatible with twisting. What do I mean by this? So of course you can choose like your twisting supercharge, and you have this pure spinor superfield A bullet. You can twist it just by deforming the differential with respect to your square zero supercharge Q, and then you can do some cohomology computation and you obtain the twisted theory. But on the other hand, you can also just take your kind of the input to the formalism, which was our super translation algebra N, now enlarged by automorphisms to G, and you can just let your element Q act via the adjoint action on G, and then you get like a DG Lie algebra. You can take its cohomology. Its cohomology are the residual symmetries of the twisted theories. However, this residual symmetry algebra GQ is again like a super Lie algebra, which has like such a consistent Z grading in degrees 0, 1, and 2. So we can take the associated positively graded P's NQ and use this as kind of the new symbol algebra of our superspace. So we can again exponentiate this to like a supergroup NQ, and we can define a distribution DQ by taking invariant vector fields and then apply the same construction again. And then the observation, which was first done by Ingmar and Brian, is that these kind of constructions are compatible. So you can, if you construct this A bullet for the super translation algebra N and then deform it by Q, you get something which is quasi-isomorphic to just constructing like this pure spinor superfield for the twisted algebra NQ directly. And this is very useful because it translates a kind of very complicated twist computation on the field theory side to like kind of a very easy computation in terms of which is basically a calculation in like a finite dimensional Lie algebra that is much more tractable. Okay, so let's apply some of these ideas to 11-dimensional supergravity and its twists. So if you take the 11-dimensional supergravity theory, it was first described in component fields where it has like geometric and a three-form gauge field with its ghost system and its antifields, and it also and then of course like fermions, which is like a gravitinum, which is subject to the Rarity-Schreier equation. You can take the 11-dimensional super Poincare algebra and investigate the space of square zero supercharges for this. If you do this, you find that 11-dimensional supergravity has two distinct twists. We will call them the minimal twist and the maximal twist. And the minimal twist is invariant under SL5, so it has 5 holomorphic directions and 1 topological direction. Naturally, if you twist in a flat background, the twisted theory lives on C5 times R. And the maximal twist has 7 topological directions and 2 holomorphic directions, so it lives on R7 times C2, and it's equivariant under G2 times SL2. So, and of course, you can either first do the minimal twist and then obtain the maximal twist as a further twist, or you can directly twist from the full theory to the maximal twist by like a maximal twisting supercharge. Okay, and then The maximal twist is kind of the smallest of these theories. We like deleted the most degrees of freedom or took invariance, took the most we were throwing the most stuff away by taking invariance. And so it's kind of maybe expected to be the simplest of these three theories. And indeed, it has a very easy geometric description. It's a Poisson Chern-Simons theory. So if we take a flat background, the BV complex, like the BV fields of this maximal twist, are just given by 0, star forms on C2 and Durand forms on R7, and the differential is given by del bar on the C2p's and the Durand differential in the topological directions. And then there is a binary bracket, which is just given by the Poisson bracket. Let's think a little bit about this kind of Poisson Chern-Simons theory and how the Poisson bracket comes along. And this is again precisely done in terms of complex geometry, basically. And then once we have our perspective established, let's try to take these kind of insights from the complex geometry and apply them to the superspaces that we were discussing just a minute ago in the full theory and in the minimal twist, and see how it kind of generalizes. So we have a Calabi-Yau twofold with then the complex structure determines a distribution like of anti-holomorphic directions, as we were discussing. And then the Durand differential now splits into del bar and del, so the 9 plus tends to 0. In addition, you have the Poisson bivector, which induces a map from 2, star forms to 0, star forms by just contracting with the Poisson bivector. And then the Poisson bracket is just given by applying the del differential and then the wedge product and then the Poisson bivector. That's all standard. And then if we take an odd dimensional real manifold, we can tensor this DG Lie algebra, which is given by a 0, star forms, del bar differential Poisson bracket with the Durand complex on this odd dimensional real manifold. And then this defines a Z2 graded BV theory, which we call Poisson Chern-Simons theory. Okay, let's try to think about how this generalizes to our 11-dimensional superspaces. We had 3 of them. We have just the full thing, like the full super-Poincare algebra gives rise to the full 11-dimensional supertranslation group. And then we have the minimal twisted version and we have the maximal twisted version. And again, all 3 of these are equipped with like the distribution given by invariant vector fields. And then we can construct these WKs, which are now analogous to K, star forms. And then by inspection, by computing this like Lie algebra cohomology, you find that in all these cases, they are concentrated in degrees 0, 1, and 2. And in addition, by computing, by explicit computation, you can see that there indeed is a pairing like between 2, star forms and 0, star forms. It's very much in the same way as we discussed it just one slide ago, and like in the case of like an actual Calabi-Yau twofold. And then you, if you have this W, you can perform like a homotopy transfer of the differential. You get a new differential D prime, which again has a grading. So D prime I goes from WK to WK plus I. And we see that there are pieces of this differential in degrees 0, -1, and -2. So again, the upshot kind of is that for the case of these 11-dimensional superspaces, this this DG algebra has very much the same structure as K like differential forms on like an actual Calabi-Yau twofold, with the difference that you have these additional differentials around. And now what we try to do is we write down some kind of generalized Poisson-Chern-Simons theory for these superspaces. And for that, we of course need the generalization of the Poisson bracket. There is such a generalization. We construct them in one of the papers. However, it turns out that this generalized Poisson bracket no longer defines a strict DG structure, but only an L infinity structure. So the differential of this infinity structure just arises by letting this degree 0 piece of the differential descend to like W0, star, which is just here is just the differential of the pure spinor superfield. That's precisely what we discussed in general already. And then you can define a bracket pretty much in the same way by, as we did for the Poisson bracket, by applying the differential in degree -1, and this kind of would be Poisson bivector. However, because this differential d-1 now no longer squares to 0, you get an additional correction, which is like the 3-area bracket, which now also involves this differential d-2. And then you can check that this defines an infinity algebra structure on this pure spinor superfield A bullet. And then we refer to these kind of BV theory given by this pure spinor superfield with the differential d0 and this L infinity structure given by mu2 and mu3 as homotopy Poisson-Chern-Simons theory.
Does this mu3 come from the homotopy transfer from the previous slide?
Yeah, it like comes from these additional pieces in the differential, which precisely are there because the distribution is non-involutive. So you get these like additional pieces. Like if you just have the case of like an involutive distribution, as for example for like an honest complex manifold, then you only have the del and the del bar differential, and they both square to 0 independently. And so this means the Jacobi identity for the Poisson bracket is satisfied on the nodes. But in this more general setting, you have these additional terms, and again, this d'-1 only squares to 0 up to pieces with up to pieces proportional to d'-2. And this means the Jacobi identity is only satisfied up to homotopy. Right. So we now have this kind of homotopy Poisson-Chern-Simons theory, which is the appropriate generalization of Poisson-Chern-Simons theory on like an ordinary complex manifold to this kind of supergeometric setting. Okay, so in the case of 11-dimensional supersymmetry, we had these like 3 different superspaces constructed from the full 11-dimensional superspace by applying the twisting procedure with respect to minimal and maximal twisting supercharges. And now we have this homotopy Poisson-Chern-Simons theory construction, and we can apply this construction to each of these superspaces. What do we get? Well, in the case of the maximal twist, we just recover ordinary Poisson-Chern-Simons theory in like a flat background. If we do this for the minimal twist, we recover some kind of homotopy Poisson-Chern-Simons theory with like an actual infinity structure, which now corresponds to like a quadratic action functional for the minimal twist. And if we do this for full supergravity, this precisely recovers what Martin Satterwall already wrote down quite a couple of years ago as a quadratic action functional for 11-dimensional supergravity in the pure spinor superfield formalism. And so the upshot of this discussion kind of is that the full theory and the twists very much have the same structure. We usually think of the twist as the twisting procedure as being something like very violent. It changes the theory a lot. But if you think in terms of twisting via this kind of supergeometric pure spinor superfield kind of way, then it doesn't do that much. It basically maps like a homotopy Poisson Chern-Simons theory to another homotopy Poisson Chern-Simons theory. It just changes the underlying superspace. And in addition, this means that this also gives some kind of new insights for the supergeometric structure of full 11-dimensional supergravity that is maybe very much non-obvious if you just start from the usual component field formulation of 11-dimensional supergravity. Namely, that you can think of the 11-dimensional supergravity theory as some kind of homotopy Poisson Chern-Simons theory for a supermanifold equipped with a distribution. All right. This concludes the second part, and in the last 15 minutes or so, I want to very briefly discuss another application which concerns conformal supergravity. All right, let's do it. So if we now take this perspective that a bullet is the appropriate structure sheaf on superspace, you can ask the obvious question, well, we have a structure sheaf, what is the tangent sheaf of superspace? Well, question is kind of answered by a definition. So a bullet is like, it's a CDGA, it has an algebra structure. So you can just take derivations of this algebra, and then the derivations are like the appropriate model for the string tangent sheaf. And we let us call this DG Lie algebra of derivations of a bullet. We will call it conf n, or the local superconformal algebra. The reason will hopefully become apparent in a minute. And then, like by the usual I guess philosophy of derived geometry, this DG Lie algebra then models like deformations of the distribution in the superspace. Like its degree 0 cohomology should have something to do with the symmetries of this distribution, and its H1 should have something to do with trying to deform this distribution. And indeed, you can perform some calculation, and then you find that if you take just an ordinary supertranslation algebra and put it into the formalism, you compute a bullet, and then you compute the derivations, so you get a model for this conf n. Then in all the examples for ordinary supertranslation algebras, like in the usual dimensions, you get the BRST complex of fields of what physicists call conformal supergravity. So you can just compute these derivations, and then you compare with some old papers in the literature, and you find that it precisely matches the field content in some magical way. And then you can also just take degree 0 cohomology of this DG Lie algebra. This then just gives like an ordinary super Lie algebra. One can show that this is the maximal transitive prolongation of the supertranslation algebra that you used as an input. In particular, if you just take like an ordinary supertranslation algebra, which was sitting in some kind of super Poincare algebra, this maximal transitive prolongation recovers the like finite dimensional superconformal algebras in all the dimensions and for all the amounts of supersymmetries where they exist. And if they don't exist, like for example in higher dimensions, you just get the super Poincare algebra and dilations. And then you can also do a third thing. You can ask yourself, well, how is this related to like ordinary conformal structures, which may be defined in terms of like an equivalence class of metric on the underlying bosonic manifold. And indeed, there is a map. You can write down a map of DG-Lie algebras from conv n to the moduli problem of ordinary bosonic conformal structures. So more precisely from there is a map from the even part of this DG-Lie algebra to the map of to the moduli problem of ordinary bosonic conformal structures. So these three properties are discussed in detail, and there are proofs for these in this paper, and we construct this map and so on. However, in the last minutes, I thought maybe it would be useful to do one particular example, what this looks like. And here I choose the example of 6-dimensional 2,0 supersymmetry. So in 6 dimensions, we have two spinor representations of spin 6. We denote them by S plus and minus. And then the R symmetry is symplectic. So for 0,2, for 2,0 supersymmetry, we have like a C4 with like the symplectic structure as R symmetry. And if V denotes the vector representation of spin 6, then the like super translation algebra is just given by N1 to be like the spinor representation times this 4-dimensional R symmetry, and N2 is just the vector representation. The bracket is induced by like the isomorphism of wedge 2 of S plus with the vector representation and using the symplectic form on the R symmetry. Right, if you do this, you can run this whole like machinery that I was introducing, and you find that a bullet is the abelian tensor multiplet. You get the like BV complex of the abelian tensor multiplet as a pre-symplectic BV theory. Once you have this, you can compute derivations of a bullet, and you find this multiplet conv n, where you also can compute the field content. So here, the like vertical grading is like ghost degrees. So you find kind of a ghost for the diffeomorphisms, which is the section of the tangent bundle T. You find a ghost for the supersymmetry, and also goes for the R symmetry, and then the physical degrees of freedom are sitting here in the second line, where you have like a symmetric tensor, which is the graviton, and then you have a gravitino, and then you have some complicated list of additional fields. For example, contains like a 3 form with some representation in the R symmetry, and some additional fermions, etc., etc. However, if you dig a little bit and you find that this field content precisely matches the component fields of the conformal supergravity multiplet that was constructed like almost 26 years ago by these by these people. And so this is like a very nice match, and you can do this. You can basically run this for all dimensions and all amounts of supersymmetry, and we did like most of the interesting examples explicitly. We computed these kind of field contents, and we compared, and we found always some matching with some kind of conformal supergravity multiplet whenever we could find some in the literature. And now again, you can basically run the same thing just for a twisted supersymmetry. So we can, for example, take the holomorphic twist of the above situation where you fix a let Q be the holomorphic twisting supercharge, and again the twist of this conformal supergravity multiplet conv n is just quasi-isomorphic to the conformal supergravity multiplet associated to the twisted supertranslation algebra. And again, you can run this like basically now finite dimensional linear algebra computation where you take the 6D2,0 superpoint Correa algebra and take cohomology with respect to the adjoint action of a holomorphic supercharge. You find that the holomorphic twist is invariant under SL3 times SP2. And if you let U be the like fundamental representation of SP2, then this twisted residual supertranslation algebra in the holomorphic twist takes this form where you have like the fundamental representation of SL3 times the fundamental representation of SP2 in the odd p's, and then wedge 2 of the fundamental representation of SL3 in the like degree 2 p's, and the bracket is just given by applying the symplectic form together with the wedge product. And so once you have this, you can again run the machinery and compute the conformal supergravity multiplet associated to NQ. And if you do this, you surprisingly, or not surprisingly, whatever your perspective is, you find the exceptional infinite dimensional super Lie algebra E36, which is given by this kind of field content where you have a zero form with values in the tangent models of basically vector field, and then some one form and some R symmetry value at zero form. So this kind of discussion then shows that the holomorphic twist of the conformal 6D2,0 supergravity multiplet is the exceptional super Lie algebra E36, which is the result in this particular example. Okay, so I think it's time to wrap up for me. Let me try to summarize the 3 main points associated to the 3 things I tried to discuss. First, I wanted to argue that the appropriate structure sheaf on superspace is the pure spinor superfield, and it precisely arises by taking into account this additional distribution, like viewing it as a non-involutive distribution, somewhat analogous to almost complex geometry, and then taking this perspective precisely leads to the pure spinor superfield. And then if you apply this to 11-dimensional supergravity, this allows you to construct the twisted 11-dimensional supergravity theory, as well as the full theory as homotopy, Poisson, Chern, Simons theories, and which finally unifies like the descriptions of the twists with the full theory. And finally, if you apply this to conformal supergravity, you very much find that conformal supergravity in this very geometric picture arises as the tangent sheaf to this superspace, and precisely as derivations of the pure spinor superfield. So it gives like a very geometric meaning to the conformal supergravity theory, namely as just modeling deformations of this distribution inside this superspace. All right, thank you very much.
Thanks, the speaker.